Statics. Definition of statics means the object is in a status of statics. What does that mean? It means the object is not moving in the x direction, or is not moving in the y direction, and is not rotating about any point. That is definition of statics. So it is staying still. That is the case with the structures or buildings. They are not mobile objects. So if you would like to take a case, an object case, and apply these rules to, and let that object be a person standing in the second floor of a building. So here's the case of a person standing in the second floor of a building, and this is standing still, is not moving. And let's apply a force to this person. Let's say this force is from this side, and this force is F1, and this person also has a weight and might be also carrying a weight, and let's name this as F3. We know from the suggestion that this person is standing still, and that is the norm. If anybody goes on the second floor and stands, normally the buildings are designed to carry these people's weight. So we see this person to stay still in his or her place, there must be an opposing force from the other direction that is opposite in direction and is equivalent in value, and let's call this F2. And the same thing happens for the weight to the weight of the person. For F3 to be balanced out, there must be a resisting force from opposite direction, must be equivalent in value and opposite in direction, and let's call this F4. So let's come to the conclusion of this situation. This person is standing still and is not moving, and there's a force F1 applied to this person from left, and he's still in place, and his weight also, which is gravity in the y direction, and he's standing still. So for this we know that F1 must be equal to F2, otherwise this person will be moving. And same thing goes for F3 must be equal to F4 for this person to stay in place. Now with these two cases, let's go and do the math. So if you'd like to do the math for the first part, if you'd like to bring F2, to this side, what we do is we say F1 minus F2 is equal to 0. That is a linear equation, a simple, straightforward equation. But let's analyze this from the forces and vectors point of view. If you look at F1, F1 is positive, right? So this means this is a force and destruction, and that is correct. That's F1. And for F2, it means a force that is going towards the west, which is in destruction. And what we're actually doing here is we are summing up these. So what we're doing here is we're having these, we're doing the sum of forces in x direction, and of course this part is equal and this is 0. So what the conclusion here is that this is the sum of all forces in x direction is equal to 0. And a matter of fact, this is the first equation of equilibrium. Now same thing happens to this side also. So again, If we would like to isolate again, we say this is equal to 0, and this is f4 minus f3. So meaning or we can fix it in this way, say f4 minus f3 is equal to 0. So again, if we would like to analyze it the same way we did, you see, if we go, this is in the y direction, so f4 is a force upwards because it is positive, and f3 is downwards, so it is negative. So again, if we take a closer look to what we did here for this part, we'll see, you'll notice that what we did is we summed all forces in y direction, and therefore this is equal, the very same story is equal, and this is 0. So what we did here actually is we repeated the very same thing. We say sum of all forces in y direction is equal to 0, and this is the second equation of equilibrium. So with this we have the first equation of equilibrium and the second equation of equilibrium. Now for this person to stay in place, also we'll apply another type of action to it, and that is the moment. So if we say, if there's a rotation, we're trying to rotate this person in this direction, and let's call this m1, and this rotation is counterclockwise, so it is positive, and this rotation is of course about this point. As far as this person is not bending or moving, there must be a resisting rotation in this direction, which is clockwise negative, and let's call this m2. So this again also, let's elaborate on this part here. So what we are doing here, we're saying that m1 must be equal to m2 for this person not to bend, right? And again, if we follow the very same way in which we analyze the previous ones, so we'll say it is m1 minus m2 is equal to 0. That's what we did. And if again we take a closer look at this, we see this is a rotation, this is positive, a positive rotation, and this is a negative rotation because of the negative sign. So what's happening here is that we're doing here is, what's happening on this part is that we are doing the sum of moments about, and call this point x, but point x is equal to 0. And believe it or not, this is the third equilibrium equation. So as a conclusion, we have sum of all forces in x direction equal to 0, sum of all forces in y direction equal to 0, and sum of moments about point x is equal to 0. These are the three equilibrium equations, and this is the third one.